Hello. So let us solve the problem now. So you see that here I have a rational function. What is my rational function? The numerator is actually 1, which is a polynomial, of course, a particular case of a polynomial. And in the denominator, I also have a polynomial. And the degree of this polynomial is 0, and the degree of this polynomial is 3, which is more than the degree of the numerator. So whenever this happens, you need to remind yourself about the method of partial fractions to integrate this function. So the first thing that we do, we factorize the denominator of this function. There is a theorem in mathematics that guarantees that every polynomial of degree greater than 2 can be factorized to factors of degree 1 and or degree 2. And this is no exception, so I will start factorizing this. So we have 1 over x to the power of 3 plus 1. The factorization, by the way, I am using this identity. Let me also remind you this identity here. So if I have the sum of two cubes, then this can be factorized as a plus b times a squared minus ab plus b squared. Okay, so here I want to give the role of a to x, and by imagining that 1 is 1 to power 3, I can give the role of b to 1. Okay, so then it becomes equal to 1 over a plus b, which in this case becomes x plus 1, times a squared, means x squared, minus the product of these two, which is x, and then b squared, which in this case is again 1. Okay, so this is what we have. And now what I do, because I have two factors involved, you see one of them is of degree 1, the other one is of degree 2, I have two partial fractions. So I will write two fractions. The denominator of the first one, I put the first factor, x plus 1. The denominator of the second one, I put the second factor, x squared minus x plus 1. And the rule is this. If you put a degree 1 polynomial in the denominator, you have to put degree 0 polynomial, which is a constant. So we don't know yet what that is, so I call it a. And here I have a degree 2 polynomial here. I have to write the most general degree 1 polynomial here. 1 unit less. Okay, this is degree 2. I have to write a polynomial of degree 1 in the numerator. And that is equal to bx plus c, because still I don't know what that polynomial is. So I use letters b and c. Now my goal is to identify a, b, and c. How should I do that? I think the easiest way is to multiply both sides of this equality by the denominator of the first side. Yes, so let me just write it here. I want to multiply everything on left and on right by this expression. Yes, so if I do that, this one that I multiply on the left will cancel that one. I am left with 1. So let me start from here. So the left hand side, only 1 is left. And then when I multiply this on the right hand side, I have to multiply it here and there. But when I multiply this here, this x plus 1 and that x plus 1 are cancelled. This is left, which is supposed to be multiplied in the numerator. I get x squared minus x plus 1. And then when I multiply this here, the denominator here is cancelled with that factor. X plus 1 survives, should be multiplied in the numerator. So this becomes plus bx plus c multiplied by x plus 1. And now what I do, I will actually expand the right hand side and write it in a standard form. I mean by writing the polynomial in descending orders of powers of x. Okay, so what I do, I multiply a in, so it becomes ax squared minus ax plus a. I multiply these two polynomials. Bx times x is bx squared, bx times 1 is bx, c times x is cx, and finally I have c. Then I write it in a standard form. So standard form means that I have to have x squared in one place. Yes, this is the highest degree that I have. So I have only these two terms involved. So what I do, I would say that I have a plus b times x squared. And then there are three terms with x here. I factor an x out. So what is left for me here? Yes, so what is left for me here is minus a plus b and plus c. And finally, I have two constant terms, a and c, so I put them together. Yes. Okay, so now what I'm supposed to do, I have to identify this with 1. So it means that a plus b, which is the coefficient of x squared, should match with the x squared coefficient here. But on the left hand side, I do not have any x squared, so this means that a plus b should be 0. And the same is true for this one, yes? So here, I do not have any x involved, so the coefficient of x should also be 0. So it's minus a plus b plus c is equal to 0. And then a plus c, which is my constant term, should match with 1. So this means that a plus c should be equal to 1. And then I have to solve this system of three equations in three unknowns. This is actually very simple. For example, from here I decide to eliminate b, so b becomes minus a. In this place, instead of b, I put minus a. I have another minus a here, so it becomes minus 2a. Yes, so this gives me minus 2a plus c is equal to 0. So this gives me c is equal to 2a. And then instead of c here, I put 2a. So this becomes 3a is equal to 1. It means that a is equal to 1/3. So this is the number that I was looking for, a. And now that I have a, you see b is minus a, so I already found b as well. So it's minus 1/3. This is my b. And finally, that I have a here as well, I can put it here and find c. c is 2 times larger than a, so it is 2/3, yes? So this also gives me c is 2/3. Okay, now what I'm supposed to do, this function, this rational expression is equal to the sum of two fractions. Now I know the constants a, b, and c. So instead of integrating this one, which is the question mark, the problem, I can integrate this and I can integrate this and add them together. Integrating these two partial fractions is easier than the original one. Okay, so what I do, I would say that, okay, my question mark is equal to the integral of this part with a equals to 1/3. So I would write 1/3 integral, and then I have dx over x plus 1. Okay, but in this case, b is minus 1/3, c is 2/3. So if you don't mind, let me factor a minus 1/3 out because I want to keep this x positive. And then if I factor that, x, the coefficient of x becomes 1, but c becomes 2. So it becomes minus 1/3 integral. For a, 1 is left. For c, minus 2 is left. And then the denominator is x squared minus x plus 1 dx. Okay, so I do not have any problems with that one. This is a very famous one. This is the ln of absolute value of x plus 1. But for calculating this one, we also have a standard trick. So this is a second degree polynomial. This is a first degree polynomial. The first thing that you need to ask yourself is that, okay, what is the derivative of the denominator? The derivative of the denominator is 2x minus 1. But of course, the numerator is not still 2x minus 1. You need to do something that 2x minus 1 appears in the numerator without changing x minus 2. So how can we do that? It is very simple. So I would say that, okay, this is x minus 2. What I need, I would do like this. So I would write 2x minus 1 first. Yeah, so let me clean this. So I will write 2x minus 1, which is the goal. I want to have this expression in the numerator, okay? But this x has coefficient 1. My x has coefficient 2. To compensate for that, I multiply by 1 over 2. But there will be another problem. So if I multiply this 2 in, of course this becomes x as I want to. But the point is that this becomes minus a half. But here I have minus 2. But that is easy. So what I should do, I would write minus 3 halves here. Okay? To compensate for that change. So you see that what I have written here is exactly this expression. Let us double check. I multiply 1 over 2 in, so it becomes x. I multiply 1 over 2 here, it's minus 1 over 2. And then I have another minus 3 over 2. So minus 1 over 2 minus 3 over 2 is just minus 2. So hopefully you agree now with me that this is another form of writing x minus 2. But what is the benefit of that? So if you don't mind, let me call this integral I. And then I would say that, okay, I is equal to the integral. In the numerator, I write 1 over 2, 2x minus 1, minus 3 halves, and then I have x squared minus x plus 1. Okay, now what and I should also write dx. So what I have to do now, I will take this one and then divide it by the denominator, minus this one divided by the denominator, and I split this integral into two integrals, one for the first part and one for the second part, okay? And then this factor of 1 over 2, of course, is a constant, so I pull it out. This factor of minus 3 over 2 is also a constant, I pull it out. So if I do all these changes, I will get 2x minus 1 in the numerator, and x squared minus x plus 1 in the denominator dx, and then I have minus 3 over 2 integral 1 over x squared minus x plus 1 dx. Okay, but now look, this integral is exactly as I wanted because it's very simple. Now you see that this is u. I engineered it in that way that if this is u, this becomes u prime. Yes, that's exactly the derivative of the denominator. So again, this becomes a logarithmic function, ln function of this denominator. So that's also easy. But for this one, so let me just continue this one. So this becomes 1 over 2 ln of absolute value of x squared minus x plus 1. Okay, minus 3 over 2, and for simplicity, let me call this integral j. So this is minus 3 over 2j. Okay, to calculate j, this is the formula that you need to remind yourself. So if I have 1 over x squared plus a squared dx, this is actually coming from the formula for the derivative of arctangent. So this is a very famous one. If a is positive, and then the integral becomes 1 over a arctangent of x over a plus a constant c. So that is the formula that I want to use for these types of integrals. Okay, but the problem is that in this formula I have only x squared and a constant square without having any x here. But in my case I have also an x, but that's also a minor thing. So what I do, I use the method of completing the square for the polynomial in the denominator. Okay, so what I do, I would say that x squared minus x plus 1 half. Okay, I want to use these two and make a complete square out of it. So what I need to make the first two terms a complete square, it is easy. I just need a 1 over 4. Yes, so I add 1 over 4 to the first two to make this a complete square, and then because I have added 1 over 4, to compensate for that I have to subtract 1 over 4, but of course you also see that you have a positive 1 here, so I will add the positive 1 there. But now look, the first three terms are actually forming a complete square, and that is x minus a half to power 2. Yes, we can check. The first one squared, x squared 2 times the first one times the second one is the middle one, and the second one squared is that one. And then of course minus 1 over 4 plus 1, I can write it as 3 over 4. Okay, so if I want to calculate the j integral, it is just integral. In the denominator, I just put this expression I just found. It is x minus a half to the power of 2. But because I want to use this, instead of writing 3 over 4, I write it as a square, a complete square. So what I have to do, I have to write square root of 3 over 2 to the power of 2, and the denominator is 1, then I have dx here. Okay, but now look, if I take this u in my head, yes, then what happens? du becomes exactly equal to dx. So what happens? It means that if I do this substitution in my head, I want to save some time, okay? So you just take this one, and then du becomes dx. So your integral becomes 1 over u squared plus square root of 3 over 2 to power 2 du. And if you compare this with the formula that is exactly the same thing, of course here u is playing the role of that x, and this number square root of 3 over 2 is playing the role of that a. So remember, I can use this formula. The only thing that I have to do, instead of x, I have u, which in this case is x minus a half, and instead of a, I have a square root of 3 over 2. Yes? So what happens? This becomes equal to 1 over a arctangent of u, which is x minus a half, over a, which is this one. And then of course this becomes 2 over square root of 3, and then this becomes arctangent. For simplicity, I multiply everything in this fraction by 2, I rescale it by 2, so the numerator becomes 2x minus 1, the denominator becomes simply square root of 3. So that is my j integral. Okay, so now I have my j integral, and I have this one. I combine them, I get my I. But remember, when I want to calculate this multiplied here, so I have to put a 3 over 2 here. This 2 and that 2 are cancelled. 3 over square root of 3 is just square root of 3. So if I, and by the way, x squared minus x plus 1 is always a positive number, yes, because the discriminant of this is negative, so this parabola does not intersect the x-axis at all, and because this is positive, it has a minimum, so it is always above. So I really don't need to have any absolute value sign. So finally, what I get for I is equal to 1 over 2 ln of x squared minus x plus 1, and then I have minus, as I explained before, I just multiply that 3/2 in, so it becomes arctangent of 2x minus 1 over square root of 3. This is my I, yes? But do you remember, in the original form, this is I have a minus a third times I, and then I also have this one, which is a third ln of absolute value of x plus 1. So if I make it a little bit smaller so that we can see, that finally my question mark is equal to 1 over 3 ln of absolute value of x plus 1, yes? And then I multiply what I got for I by a third, so this becomes minus 1 over 6 ln of x squared minus x plus 1, and then plus square root of 3 over 3 arctangent of 2x minus 1 over square root of 3, and of course I can add a constant at the very end. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.